Somewhere in a galaxy, hundreds of millions of light years away, a black hole did something scientists say should not happen. It sent out a rhythmic burst of energy over and over, like a heartbeat, from an object that by definition is not supposed to let anything escape, not even light. NASA and a network of orbiting X-ray observatories caught it happening in real time, and the readings do not fit cleanly into the physics we thought we understood about how black holes behave. This is not a rumor, this is not a fringe theory, this is a documented repeating signal coming from the edge of one of the most extreme objects in the universe, and right now astrophysicists are racing to explain it. Before we go further, if discoveries like this genuinely interest you, take a moment to subscribe, because this channel exists to dig into exactly these kinds of stories, and there is much more coming. To understand why this signal is so strange, you first need to understand what a black hole actually is, because the popular image of a black hole as a simple cosmic vacuum cleaner is not accurate. A black hole forms when a massive star collapses in on itself, or when matter piles up so densely that its own gravity overwhelms every other force holding it apart. What results is a region of space where gravity is so strong that the escape velocity exceeds the speed of light. Nothing, not light, not radiation, not matter, can escape once it crosses that boundary, known as the event horizon. That is the defining rule of a black hole. Once something crosses the event horizon, it is gone from our observable universe forever. So when instruments detect energy coming from the direction of a black hole, that energy is not coming from inside it. It is coming from the extreme environment surrounding it, the swirling disk of superheated gas and dust caught in the act of falling in, known as the accretion disk. This region gets so hot, in some cases hundreds of millions of degrees, that it glows brilliantly in X-rays long before any of that material actually crosses the horizon. For decades, scientists have studied this glow to understand black holes indirectly, since we cannot observe the black hole itself. What changed recently is the pattern of that glow. Researchers using X-ray telescopes, including instruments associated with NASA's ongoing black hole monitoring programs, detected a signal from a supermassive black hole that pulses on a regular repeating cycle, brightening and dimming in a rhythm that should not be possible given everything we understand about how accretion disks behave. If this is blowing your mind a little, that reaction is exactly right, because scientists reacted the same way. Go ahead and hit that like button right now. It costs nothing, and it helps this video reach more people who love these deep dives as much as you do. This category of event has a name. Astronomers call it a quasi-periodic eruption, and it was barely on anyone's radar until a handful of these events were caught by X-ray observatories in recent years. The pattern is unmistakable once you see it. The black hole surroundings brighten dramatically in X-rays, fade back down, and then repeat the cycle again, sometimes on a timescale of just a few hours, with a regularity that looks almost mechanical. More like a lighthouse beam sweeping past than the chaotic, random flickering scientists expected from matter falling into a black hole. The leading explanation researchers have proposed is almost as strange as the observation itself. Some scientists believe these eruptions happen when a smaller object, possibly a compact star or a stellar remnant, is caught in a tight orbit around the supermassive black hole, repeatedly plunging through the surrounding disk of hot gas on each pass. Each plunge disturbs the disk, releasing a burst of X-ray energy. And because the smaller object's orbit is regular, the resulting flashes come at regular intervals too. If this explanation holds, it means we are not just watching a black hole glow. We are watching a smaller object being slowly devoured, one orbit at a time, each pass sending out a signal that reaches us hundreds of millions of years after it left its source. Here's where things get even more interesting. When researchers looked closely at the timing and intensity of these pulses, some of the data did not fit the simple orbiting object model cleanly. In certain cases, the pulses changed in strength and spacing in ways that suggested something more complex was happening near the black hole, possibly instabilities in the accretion disk itself, or interactions between multiple objects orbiting close to the event horizon at once. This is the part where the phrase breaks physics needs to be handled carefully, because no observation has actually violated the laws of physics as we understand them. What has happened is that the observation does not fit our existing models cleanly, and when that happens in astrophysics, it usually means our models are incomplete, not that gravity or thermodynamics have stopped working. If you are new to this channel, we cover exactly this kind of story every single week. Real missions, real data, and the scientists working to understand what it all means. From Voyager's interstellar signals to James Webb's discoveries at the edge of our solar system. Subscribe now so you do not miss what comes next. To understand why this matters so much, it helps to step back and look at how strange black holes already are before you even add a mysterious pulsing signal into the mix. Supermassive black holes, the kind found at the centers of galaxies, including our own Milky Way, can contain the mass of millions or even billions of suns, compressed into a region smaller than our solar system. The black hole at the center of our galaxy, known as Sagittarius A star, was directly imaged for the first time in 2022 by the Event Horizon Telescope, a global network of radio observatories working together as a single Earth-sized instrument. That image, a glowing ring of light bent around a dark central shadow, was the first direct visual confirmation of what theoretical physics had predicted for over a century. It also confirmed something important for this story, that the region immediately surrounding a black hole behaves in ways that are extreme, dynamic, and in some respects still not fully understood, even with the best instruments humanity has ever built. So when a repeating X-ray pulse shows up from a distant supermassive black hole, scientists do not dismiss it as noise. They treat it as a rare, direct window into physics happening in one of the most extreme gravitational environments in existence, a laboratory no human could ever build, operating at scales and energies far beyond anything achievable on Earth. Drop a comment below and tell me, if you could send a probe close enough to safely observe a black hole's edge without being pulled in, what is the first thing you would want it to measure? There is another layer to this discovery that connects it to one of the deepest unsolved problems in modern physics, something called the black hole information paradox. According to Einstein's general relativity, anything that falls past the event horizon is lost completely, its information erased from the observable universe. But according to quantum mechanics, information cannot simply be destroyed. It has to go somewhere, even in the most extreme circumstances. This contradiction has puzzled physicists for decades, including Stephen Hawking, who spent much of his career wrestling with it. Hawking's own theoretical work suggested that black holes are not entirely black at all, that they slowly emit a faint form of radiation, now called Hawking radiation, as a result of quantum effects occurring right at the edge of the event horizon, over unimaginably long timescales. This radiation causes black holes to lose mass and eventually evaporate. Though the process is so slow for a supermassive black hole that it would take far longer than the current age of the universe to complete. Hawking radiation itself has never been directly detected. It is far too faint given our current instruments, but the theoretical framework behind it fundamentally changed how physicists think about the boundary between a black hole and the universe outside it. Repeating eruptions like the one just observed do not solve the information paradox, but they give scientists new real-world data about how matter and energy behave in the immediate vicinity of an event horizon. Data that any future theory will eventually need to account for. If your mind is being blown right now, make sure to share this video with someone who loves space as much as you do. It genuinely helps this channel keep making videos like this. Let's talk about the instruments actually responsible for catching signals like this, because they matter as much as the discovery itself. X-ray observatories cannot function the way optical telescopes do here on Earth's surface, because our atmosphere absorbs X-rays before they ever reach the ground. That means every X-ray telescope capable of observing events like this has to operate from space. NASA's Chandra X-ray Observatory, launched in 1999, and the European Space Agency's XMM-Newton, launched the same year, have spent more than 2 decades scanning the sky in X-ray wavelengths, building an enormous archive of data on flaring, erupting, and pulsing sources across the universe. More recently, newer instruments have been specifically designed to catch fast, repeating events like quasi-periodic eruptions as they happen, rather than relying on catching them by chance during unrelated observations. This is precisely why so many of these strange pulsing black holes have only been identified in the last few years. The events themselves may have been happening for as long as these black holes have existed. We simply did not have instruments sensitive enough or watching frequently enough to catch them in the act until relatively recently. That timing matters. It means we are not looking at a new kind of physics suddenly appearing in the universe. We are looking at physics that has always been there, only now becoming visible because our tools have finally caught up to it. NASA has taken this category of discovery seriously enough to prioritize follow-up observations whenever a new quasi-periodic eruption is identified, coordinating between multiple space telescopes to capture the same event across different wavelengths simultaneously, building a more complete picture of what is actually happening in these extreme environments. There is a broader historical pattern worth mentioning here too, because this is not the first time a black hole observation has forced scientists to revise their assumptions. When the first gravitational waves were detected in 2015 by the LIGO Observatory, the signal came from two black holes colliding and merging into one, an event so violent it briefly outshined every star in the observable universe. In terms of pure energy release, all of it invisible to ordinary telescopes and detectable only through the ripples it sent through the fabric of space-time itself. That detection confirmed a prediction Einstein had made a full century earlier, one he himself doubted could ever actually be measured given how impossibly faint the ripples would be by the time they reached Earth. Every major black hole discovery since then, from the first image of a black hole shadow to these newly identified quasi-periodic eruptions, has followed a similar arc. A strange signal appears. Existing theory struggles to fully explain it. And slowly, through careful observation and repeated testing, our understanding expands to accommodate it. Black holes have a long history of teaching us more about physics than almost any other object in the universe, precisely because they represent the most extreme conditions gravity, matter, and energy can reach without collapsing our current framework entirely. It is worth pausing here to address something important, because we always try to be precise rather than sensational. Scientists have not declared that this discovery overturns general relativity, and no credible researcher is claiming these observations disprove Einstein's physics. What researchers are saying is that the behavior does not match the simplest existing models of how accretion disks and orbiting objects should interact, and that more data is needed to determine whether the explanation lies in orbital dynamics, disk instabilities, or something not yet fully theorized. This is exactly how real science works. A surprising signal comes in, researchers propose an explanation grounded in existing physics, and then that explanation gets tested, challenged, and refined over months or years, not settled in a single announcement. Quick request before we continue: if this video has taught you something new, tap that subscribe button now. It costs nothing, and it directly determines whether we can keep making deep dives like this one. There is also a practical side to why NASA and its partner agencies invest so heavily in tracking events like this. Every repeating eruption captured gives researchers a natural, repeatable experiment, something exceptionally rare in astrophysics, where most objects of interest are either one-time events, like a supernova, or so slow-moving that meaningful change only becomes visible over decades. A black hole producing a predictable pulse every few hours means scientists can plan observations in advance, coordinate multiple telescopes across different wavelengths to watch the exact same moment simultaneously, and directly compare data from one eruption to the next to see what stays consistent and what changes. That kind of repeatability is what allows a single strange signal to evolve from an interesting anomaly into a genuine scientific case study. And it is part of why this particular discovery has generated so much attention within the research community, even though the public conversation around it is still relatively new. Let's also talk about why this particular black hole was chosen for such close monitoring in the first place. Not every black hole shows this kind of activity. Most supermassive black holes at the centers of galaxies are relatively quiet most of the time, slowly accumulating gas and dust without producing dramatic, regular signals. The ones that do show quasi-periodic eruptions tend to share certain characteristics. often sitting in smaller, otherwise unremarkable galaxies, rather than giant, active galactic nuclei with enormous jets blasting outward. This makes the eruptions even more valuable scientifically because they offer a relatively clean laboratory, a black hole not overwhelmed by the chaos of a fully active galactic nucleus, where researchers have a better chance of isolating exactly what is producing the pulsing signal without other extreme phenomena muddying the data. Some researchers have proposed that these quieter black holes caught mid-eruption may represent an early or transitional phase, moments where a black hole's environment is being actively reshaped by an object, spiraling ever closer on its way toward eventual consumption. If that is correct, catching one of these eruptions in progress is something like catching a fossil in the process of forming, a rare chance to observe an ongoing process rather than only its aftermath. It also raises a sobering thought about timescales. The light and X-rays carrying this signal left their source hundreds of millions of years ago, long before humans or even most complex life on Earth existed. Whatever object is being consumed near that black hole right now, in our present moment, finished that process an unimaginably long time ago. We are not watching a live event unfold in real time. We are watching a message arrive, one that has been traveling across the universe since long before our own planet's history as we know it began. So let us bring this together. A supermassive black hole, hundreds of millions of light years away, is emitting a repeating rhythmic burst of X-ray energy that does not fit cleanly into existing models of how black holes and their surrounding disks are supposed to behave. The leading explanation involves a smaller object locked in a tight repeating orbit, plunging through the black hole's surrounding disk on each pass and triggering a fresh burst of energy every time. Some of the observed data suggests the environment near the black hole may be more complex than that simple picture allows, possibly involving disk instabilities or multiple interacting objects. None of this violates the laws of physics as we understand them, but it does reveal gaps in our models, gaps that researchers are now racing to close using some of the most sophisticated space-based X-ray instruments ever built. And it connects, even if only indirectly, to some of the deepest unresolved questions in modern physics, including how information behaves at the edge of a black hole and what Hawking radiation might one day teach us about how these objects end. This is not a story about physics breaking. It is a story about physics being tested at the most extreme boundary conditions found anywhere in the observable universe, and about scientists patiently building the tools needed to watch it happen in real time instead of only theorizing about it from a distance. If this video has taught you something new today, please take a moment to subscribe, because we are going to keep following black hole research as new data comes in. And there is still so much more to learn about what happens at the true edge of the unknown. So here is the question I want to leave you with. If astronomers eventually confirm that a compact object really is orbiting inside that black hole's disk, slowly spiraling closer with every pass, do you think we will get to watch its final plunge in real time, captured by the same instruments recording this rhythmic signal today? Or do you think the true answer to what is happening near that event horizon is still something we have not even theorized yet? Type your answer in the comments below. I read every single one, and I genuinely want to know what you think. If you enjoyed this journey into one of the strangest signals ever recorded from a black hole, do 3 things before you go. Like this video so more people can find it. Share it with someone who would find this as fascinating as you did. And subscribe so you are here for every update on this story and every other deep space discovery still waiting to be uncovered. Thank you for watching,